Okay, good afternoon. So we will good afternoon. Yeah. So we will continue with what we have seen in the last class. So we were just introduced with the dynamics part of rigid body mechanics, and you have understood that that would be studied in two ways. First, we will look at kinematics, that's only motion geometry, and then we will look at kinetics, that's a real dynamics, wherein we require to write the governing equation, that is essentially Newton's second law or Euler equation, according to the situation. And also we were very much aware that we do this rigid body mechanics with two ideology. One is particle ideology, another one is rigid body mechanics. So particle ideology is not a tiny particle, massless particle. It is a rigid body where we can make sensibly assumption that the physical geometry can be neglected. That's exactly is what we have seen, that a big airplane path in the air you want to trace, then you can neglect its physical geometry, and that is what is called a particle mechanics. So the advantage of having particle mechanics is the effect in a body which is accelerated is only undergo translation. Whereas if you are considering physical geometry, then you will have a detailed motion. That is, it will have a translation, or it can have only rotation, or it can have combination of translation and rotation. So this is what is the basic understanding that you should have with your rigid body dynamics. So we have ended with looking at what are the kinematic equations of a rigid body. So we have seen there are three primary motion equation and three secondary motion equation. So I'm going to start from that same point, and today's lecture we are going to look at what do you mean by motion curves and how can we make use of that to predict its complete motion. So that's what we are going to look at in today's class. So let me share my screen for that. Are you able to see my Active Inspire board? Just it is not yet come. So this is lecture number 34. And today it is 14th October 2020. So what we are going to study today is that we know that kinematic equation basically, because we have defined what are motion parameters, that is position of an accelerated body with reference to a fixed reference, and then displacement, and then velocity, acceleration, and another differential called jerk. We are going to have, these are all what is defining motion parameter, which are function of time. We are going to only look at these are the four parameters in our rigid body mechanics. Their definitions are this is to refer a position of a moving or accelerated body in a path with respect to a fixed reference. So let us call x is any time, t its position. So what is displacement from start at any instant? If you look at it, is the difference between x minus x naught. This what is displacement. What is velocity? Velocity we defined as dx by dt. And what is acceleration? We defined as dv by dt, or it can be d squared x by dt square. Or we can also write this acceleration as implicit function of time, that is v dv by dx. And what is this jerk? Let us just understand what is a jerk, but we may not be solving problems. That is derivative of acceleration with respect to time. So it is going to be d squared v by dt square, or d cubed x by dt cube. So this is what is definition of jet. So this all is because of time, and we have position, velocity, acceleration, and the radial relations are forming three primary motion equations. What are those? X is function of time, velocity is function of time, or acceleration is function of time. And you also have a radial relation, which are called secondary motion equation. So you have v as function of x, and you can represent a as function of x and a as function of v. So if you look at v as function of x means what? What is the velocity of accelerated body as it progresses in its path? So if I look at a straight motion, rectilinear translation, at any position of a rigid body, what is its velocity if I describe? That is v as function of x. Similarly, you can represent x as function of a as function of x or a as function of v. So at this particular velocity, acceleration is this, like that. If you say these are the equation, secondary motion equation, these are primary motion equation. So this is in generic 6 equation to describe your kinematics of kinematic equation. These are called the kinematic equation. Equations of motion. You should differentiate this equation from fundamental governing equation of motion. What are fundamental governing equation of motion? Equation of motion, that those are two. One is sigma f is equal to ma, sigma m is equal to I alpha. So these are fundamental governing equation. So this will be accounted in kinetics. In kinematics, we are only interested in motion geometry without considering cause of the motion. So this 6 equation again going to be very specific according to the situation. So if v happens to be constant, that means there is no acceleration, and then equation is only one equation. That's what we call it as a uniform motion. Yesterday we have seen. So what would be the equation? So it is v is constant, that means dx by dt. So that gives you 0. So you will write simply v constant, so dx is equal to v times dt, and you are able to have x is equal to x naught plus vt. So if x naught is 0, what I mean by x naught is 0, if I look at the path, and this is my reference where x naught is 0, and at any time at t0 it is at the origin, and then it moves, this becomes 0, then my equation is simply x is equal to vt, and v is constant here, and this is called uniform motion. And it is in a straight path, so it is a rectilinear uniform motion. That's a special case. So for uniform motion, out of 6 equation of kinematic equation, only one equation sufficient, that is simply x is function of time. That's all. This is only equation you require, right? And then other special case is what, when acceleration is not velocity is not constant, it is also varying with respect to time, means dv by dt exists, that is acceleration. If that acceleration happens to be constant, if this acceleration happens to be constant, then it is again a special motion called uniformly accelerated motion. Uniformly accelerated motion that we have seen yesterday. So we had 3 equations. What are those 3 equations? So first equation is x is function of time. So that is nothing but x is equal to x naught plus v naught t plus of at square. I'm not going to derive this again. We have derived that in the last class itself. And then we looked at v can be function of time. So 2 primary equations that I will have. So v is equal to v naught plus at. And then I will have v is equal to function of x. So that's essentially V squared is equal to V naught squared plus 2 into A into x minus x naught. So these are the three equations that are describing special motion called uniformly accelerated motion, where acceleration is constant. In case acceleration is not constant, then you will have all the 6 equations necessarily to be expiring. So for uniform motion, there is no secondary motion equation, it's only primary motion equation. X is equal to function of time. For uniformly accelerated motion, out of 6, you require only 3 equations. So out of 3, 2 primary motion equation, 1 secondary motion equation. Why? Because in this equation, you do not see the explicit appearance of time. So that is why it is secondary motion equation. And then in case the acceleration is not equal to constant, it is varying, then you require all the 6 equations that are described here. And then you'll have to essentially use to find out that is if A is not equal to constant, you should use your definitions. What are the definitions? So acceleration is going to be dv by dt, where A is function of time, V is function of time. So I will have A of t dt equals dv. So I can integrate this, I can have my motion parameters variation. And you can also express A as function of d squared x by dt square, or A is equal to v dv by dx, where this A is not constant, A is function of time. In this, A equals function of time. So I'll have to use an integral approach and get my other motion parameters. So what do you mean by complete description of motion? I should be able to define at any point of time what is the position of the accelerated body, velocity of the accelerated body at that time, and acceleration of the body at that time. All I should be able to explain. So that's what is called complete description of motion of an accelerated body. So if that is so, today's class we are going to look at what are motion curves. So what are motion curves? The variation of this motion parameters is function of time. That are primary motion curves. So A as function of time, V as function of time, and X as function of time. So variation of X as function of t. So I'll have to plot these graphs. These plots are going to give me motion curves. They are not an actual path. The variation of this parameter, position, velocity, acceleration, as the course of time, as the time progresses. That curve is not an actual path. That you need to understand. So these are called primary motion curves. So now let us look at what are these primary motion curves for the 4 motions that 4 equations that we have got. For uniform motion, what would be my curve? I know only it is X is function of time. For uniform motion, what is my motion curve? It is only variation of X as function of time. So I'll have time axis. I'll have here X, and I have t is equal to 0. It is not. So this is my path. This is my path, and this is my reference X. 0, O, 0, 0. Then I have my t is equal to 0. This is my x naught. Here is what it's starting. So this is t equals 0. From here it starts. That means I'll have here this point. And my equation is what? X is equal to x naught plus vt. So v is constant. So I will have a straight line equation. So this is what is x equals x naught plus vt. This curve is what is called a motion curve for uniform motion. So at any time t, so at t is equal to 0, see what I get is x naught. So this value is x naught. X naught is position in the fixed reference. So the reference fixed point is O here, and x naught is the starting point. So from here my vehicle starts moving in this line. If I say, then it's fine. This is what is uniform motion, and it's moving how? It is moving with the constant velocity. Constant velocity. So if I have to plot my Vt graph for uniform motion, V is constant, so I will have that value of V. So V is constant. So this is what is my motion curves. So what would happen to the acceleration? Since v is constant, acceleration is zero. Acceleration is zero. So acceleration here is zero on this line itself. Zero acceleration, right? This is what is variation of our motion curves for uniform motion. So how the plot for uniformly accelerated motion will appear? Uniformly accelerated motion. How will it be appearing? So I have to plot xt. T is x. So what is my equation? X is equal to x naught plus v naught t plus half a t square. That's an equation. That's the equation when a is constant. See, now this is having degree 2. It's a parabolic curve. So at t is equal to 0, x is x naught. So I'll have somewhere here. My curve starts x naught, and then it's varying with the 2-degree parabolic variation. So it will be going like this. So this is what is my x naught plus v naught t plus half a t square. What is x? Right? So this is the variation. So this is the variation of x as function of time. What is the variation of velocity? Velocity that we had, velocity is equal to v naught plus at. So v naught is an initial velocity, v naught, and it is going to vary like this. So it's a straight line. So here it's degree 2 and this degree 1, t power 1. And this is what is its acceleration, a. Slope is what is its acceleration. So this is a variation of velocity as function of time in uniformly accelerated motion. So what is its acceleration? This is t and this is acceleration, and acceleration is constant here because dv by dt is v naught is constant, so it is only a. So dv by dt equals a, which is constant. So that value will be a constant value. So that is all. So this is what is called motion curves. So if I have my motion of a rigid body described by these equations, that motion is what is called continuous motion. Continuous motion. Why? Because from the start till the end, any time, I describe the motion only by one single equation, which is differentiable or integrable. We can do integration of the equation. That is why it is called a continuous motion. We also have another classification of motion called the erratic motion. What do you mean by erratic motion? I will have my observation of accelerated body in a time where I will have time steps or time intervals, where in each interval I will have a specific equation describing motion parameter. So the motion curves in a given time interval are different, then it is an erratic motion. So example of erratic motion is that you go to theme park and there you are playing with the different games. So if you are sliding on a slide which is spiral, say for example, or you are sliding from a slide and then you have a different motion. Suddenly you feel more acceleration, suddenly you feel constant acceleration, sometimes zero acceleration. So like it will be varying. So it is not that same experience from start till end of the event you will have. So that is an example of erratic motion. So let us look at some problems and use this motion curves to describe the complete motion, so that you will understand what are this physical meaning. Right? So let me take an example problem. So consider a bicycle is moving along a straight line. A bicycle is ridden along a straight line such that its position is described by the graph I am going to plot. Construct Vt and At graphs between 0 to 30 seconds. That's a question, right? So motion of bicycle. Of a bicycle is described as follows. So what is it? Its position. So it is moving in a straight path. So it's straight path. Say this is its point O and moves in the straight path, and this is X. Rectilinear translation we are going to consider. So the variation of this is given as between 0 to 30 seconds. 0 to 30 seconds. But in this 30 seconds, you see that is described with different motion curves. So till 10 seconds, you have the variation of that is given by a parabolic variation. After that, it has been given by a straight line. Right? Like this. So here it is x equals t square, and here it is x equals 20 t minus 100. So that is all. So now what is my position at x is equal to, at t is equal to 0, at t equals 0, what is x naught? T is equal to 0, x naught is 0. So that is why it is starting from 0, right? So in this interval, what is the interval? It is from 0 to 10 seconds. 0 to 10 seconds. X naught is this. What is x 10? So it is 10 square. It's 100 meters. So it is 100 meters here. So this position value is 100 meters. So position is in meters. What I mean by that, at t is equal to 0, the bicycle starts from this point O, and in 10 seconds it is reached 100 meters. So here it is 100 meters in a straight motion, right? That's the meaning. After that, what's happening? It's varying again like that, but it is described by another motion. So here the variation is parabolic variation, but here it is linear variation with respect to time. So see, you can check when t equals 10 seconds, if I substitute in this equation, it satisfies at this point, both the equations satisfy. So if I put 10 here from this equation, that means what I have to take now the interval 10 to 20 or 30 seconds, 30 seconds. If I consider now x10 is what in that equation, 20 into 10 minus 100, so which is 200 minus 100, again 100. So at this point you have from this equation same, and then when x is 30, then it is 20 into 30 minus 100, so I get 500 meters. So this is 500 meter. 500 meter. Also in 30 seconds, the cyclist ride the cycle where he goes is 500 meters. So that is what is the description of the motion, right? So this is our observation time. So after 30 seconds, what is happening? We do not know. He could have stopped the vehicle or a bicycle or something, but this is the observation time given. If this is so, you are asked to find the complete description of motion of your cycle ride. Then you should find variation of velocity as function of time, variation of acceleration as function of time. That's what is our task. So what do you have to do? Now you have to plot the variation of velocity, which will be meters per second, as function of time. Right? So in this interval, now what is my velocity? I have my position variation is given by t square. So dx by dt is what is my velocity. So that's 2t. So v equals 2t is what is my equation. So v is equal to 2t is what? It's a straight line passes through its origin. So I will have here my equation goes like this till this 10 seconds. So I just to draw, see this, the way I draw the diagram, I have to draw this one below the other. I have to take the same scale on here as well. I should project those points. So I expect that in your FAT examination, when you are asked the question or in your assignments I am going to post, you should follow the same way. How do I solve? So this is 10 seconds. Now what would be my velocity? So v subscript 10. So any motion parameter like x subscript 10, v subscript 10 or a subscript 10, if I put, the subscript represent time always in our dynamics. So v10 will be 2 into 10, which is 220 meter per second. 20 meters per second. So I know that now this is 20 meters per second. And this equation is v is equal to 2t. Now what is this equation? See here it is with the linear variation. So I know between this interval, my position is given by 20t minus 100. So dx by dt will be 20. That's all. So 20 which is constant now. So what I mean by that? What do you mean by that? From here on, it is of constant velocity motion. This is uniform motion now, because velocity is constant. So what is that meaning? The cyclist gain his maximum speed of the vehicle in 10 seconds, and he maintains to continue with the same speed. So that's exactly what will happen. So when you start driving, riding your cycle, you do that. You take the stand out, then you pedal, start your bicycle motion, and then you put your maximum energy in a straight track when you want to drive, and then you maintain that for further cycling. That's the meaning here. So you can also have, instead of bicycle, an athlete starts his motion and he is putting its maximum energy, converting his complete stamina into maximum kinetic energy, and he attains his maximum velocity with the shortest time, and then he completes the remaining with the same energy level. The same energy level is running. So if a person is converting his potential for 10 seconds to complete his 100-meter race, he may not be able to achieve it. So the acceleration should be so quick, it should be more, so that he can quickly gain his maximum velocity with which he can run, and then he maintains and then finish the race will be leading him to winning. So you can also think instead of bicyclist, an athlete running on a 100-meter track, the similar kind of motion curves. We have anyhow not finished. So what is the complete description? What is missing now is an acceleration variation. So when I look at acceleration variation, this is time, and I have here acceleration. The unit of it is meter per second squared. And you see now here this linear variation. So I know acceleration is defined as dv by dt, and I know velocity is v is equal to 2t. So that is going to be simply 2 meter per second square, which is constant. So that's what is uniformly accelerated motion. So the cyclist, the cycle ridden by the cyclist is undergoing uniformly accelerated motion for first 10 seconds. After that, it is going with the uniform motion. So your acceleration is 2 meters per second constant for this period, and then it is 0 further, because you see here what is your velocity? Velocity is constant here. V in this zone is constant, 20 meters per second. So v equals 20. So dv by dt, which is a, equals 0. That's what is here. So there is no acceleration at all. So this is what is you are describing as a motion curves. And this motion curve is a function of time. This is not an actual path. What is your actual path? Your actual path is this. Here is drawn. So point O is the reference point from where the cycle starts from rest, and then from there on it goes with the velocity along with this. So the variation of velocity is uniformly varying till 100 meters. After that it is constant. So how do I get my secondary motion curve? So if I have to plot my variation of velocity as function of xa. So here it is 100 and here it is 500. It's an actual path. So you know, for the first 100 meters, what is my velocity? Velocity is now varying. Velocity is now varying. right? And after that, what is that? Velocity is constant. So velocity is constant from here, and the velocity is varying here. So this variation is linear variation or non-linear variation, that you should understand. So here, how do you get that? You have to eliminate time from this. So here it's what is v is equal to 2t. So at t is equal to 10 seconds, you get 20 meters per second. So that variation is changing. So how do you get that? Here you can say that this is going to be constant because you also have your definition of acceleration as v dv by dx, right? So dv by dx is what is something called a velocity gradient, you can say, or the slope here you could say. So since acceleration is constant and the slope here should be dv by dx into velocity is constant. So this slope also is constant. So slope is constant when the variation of x, v as function of x is linear. Then only I will have dv by dx constant, because v here is what? V is varying. How do I express that? So is this plot correct? V as function of x, v is varying like this. After that, v is constant. So first 100 meter, the variation of v as function of x is linear. Is that correct? Do you follow? So how do I get that? I have v is equal to 2t. What is this variation?
It should be parabolic, sir.
Yeah, so you have to, that's why I was asking you. So v equals 2t is what is velocity variation function of time, and position is varying as t square. So now I have to express v as function of x. So what I have to do, I have to put what is my t here. So t is v by 2, so x is equal to v by 2 whole square. So I will have v squared by 4 is what is x. So the variation of v is now 4x under root. So this is the variation. So this is not varying linearly. So it will be varying like this, right? So v is going to vary as function of 2 root x. So when x is equal to 0, it's 0. When x is equal to 100, it is 20. But this variation is with this. So that's what you are asking. So here v equals 2 root x. That's this equation. And here v equals constant. So this curve is what is called the secondary motion curve. Here is what you are able to see physically, what is the velocity of the cycle as you go along the path. Whereas primary motion equation, not referring to the path, it is referring to the motion parameter. How does it vary as function of time, right? So this is what you should understand. So now let us have another 2 more problems.